Alright, this is the final video on strategies of integration, and this is actually the last real problem before extra credit that I actually had on that final test. Let's go ahead and do both. Now this right here, we should recognize the relationship between x plus 1 and x squared plus 2x plus really anything after that, right? Because this right here is the beginnings of x plus 1 squared. So if we rewrite this, it's going to give us a little more insight into exactly what I need, okay? Now, what I have here is I have basically the makings of Trig Sub, right? Because, you know, as long as that x plus 1 is in those parentheses, that's one term. So what I have underneath this radical, that is a binomial. And I know that if I can substitute trig in, especially the right trig, I know that I can get basically a Pythagorean trig ID to help me out. So I'm going to let tangent theta is equal to x plus 1, and therefore secant squared theta d theta is equal to dx. So what I then have is I have tangent theta for this x plus 1. I have tangent squared theta underneath the radical, and for this dx over here I have secant squared theta d theta. Now, this tangent squared theta plus 1 is going to become secant squared theta underneath the radical, and that is going to combine, it's going to become secant theta when it pulls out, and combine with that secant squared to become secant cubed theta d theta. Now, that should harken back to what we did in terms of trigonometric integrals in 7.2, and you should recognize the fact that you can basically pull the secant squared out here and reserve secant tangent for your du. That winds up being u squared du, so I have 1/3 secant cubed theta plus c. Now I simply need to create my triangle. Okay. And I have theta right here. Now, the original was x plus 1 over 1, and so it should come as no surprise that this is x squared plus 2x plus 2 over here. Now, that gives me hypotenuse over adjacent, but I need to cube it. And so when I cube a square root, it's simply going to turn it into the radicand to the 3/2. And there we go. Alrighty, let's go ahead and take a look at this one. Now we're going to be using a similar strategy here, and I'm sure that doesn't surprise anybody. So go ahead and think through how you want to change that radicand in the denominator. And it should, of course, accord with the structure right here, okay? And so we get x dx, and underneath the radical we have x squared plus 6x plus 9, and then a 3 left over. Okay, since that was obviously off the screen, I'm going to go ahead and leave that there. So basically we take our x squared plus 6x as our indication of what perfect square needs to be, and then of course 12 has 9 inside of it with 3 left over. So what we're going to do is we need this under here to be 3 tangent squared. So we know that x plus 3 needs to be √3 tangent theta. Because when it's squared, it becomes 3 tangent squared. Now that means that x, this x in the numerator is what I'm thinking about, needs to be that, right? And so dx is simply √3 secant squared theta d theta, And of course, thinking about my triangle a little bit down the line, that's going to be x plus 3 over root 3, and that's going to be the ratio that I'm going to use. So let's keep all of that in our head as we basically replace the x with the theta. X in the numerator, like I said, becomes root 3 tangent theta minus 3. Dx becomes root 3 secant squared theta d theta. I love how like the simplest of numerators can become this monstrosity right here. When I plug this in, this becomes 3 tangent squared theta plus 3. That becomes 3 secant squared, or root 3 secant theta when I pull it out. Now that secant cancels with one of those in the numerator. That root 3 cancels with that root 3. And what I'm left with is root 3 secant theta tangent theta minus 3 secant theta. And all I did was basically just distribute this secant across this binomial. Now, what that does is that gives me two relatively simple integrals, as long as I remember the formula for the integral of secant theta. And so I get root 3 secant theta minus 3 natural log secant theta plus tangent theta plus c. Now, this right here, and we're going to have to go ahead and create our triangle. And that is x plus 3 over root 3, and that winds up, of course, being x squared plus 6x plus 12 underneath the radical. And so we get root 3 x squared plus 6x plus 12 over root 3, because that, of course, is our secant, our hypotenuse over adjacent. And this winds up being secant plus tangent. Well, both of those have a denominator of that root 3, so we're going to go ahead and 6x plus 12 plus x plus 3, all of that over root 3 plus c. Now remember, we've done this before. Because this can be split apart into 3 natural log of the numerator minus 3 natural log of the denominator, and you have to distribute the negative, of course, so it's actually plus 3 natural log root 3. It doesn't matter whether it's positive or negative, because 3 natural log root 3 is a constant, right? And it can just be absorbed into c. So the moment that I'm going to rewrite this, okay, I need to go ahead and clean up this by simply getting rid of the denominator. And by getting rid of the denominator, I'm basically saying I'm using properties of logarithms in order to turn this into 2 separate logarithms, and that constant that gets pulled out just gets absorbed into this original c and becomes a different c, or a c that is just as arbitrary as the first one. Okay, now that's all of the questions of the last 2 tests that I gave on this topic, but there are a couple of extra credit problems that I gave along the way, and let me go ahead and let's go over this one right here. Now, this one looks pretty innocuous, but it actually winds up being a little bit of a pain. Okay, now it looks like trig sub, and it is. Okay, so obviously we want x equal to 3 tangent theta, because that means x squared is equal to 9 tangent squared theta. We know that dx is equal to 3 secant squared theta d theta, and just for the future, we're gonna go ahead and stipulate that tangent theta is equal to x over 3. Now, that is all the stuff that I'm going to use for substitution and for constructing my triangle just a little bit later. So let's go ahead and let's recreate this integral in terms of theta. We get 9 tangent squared theta plus 9. That's the numerator right here. And then we multiply by dx, and we're going to pop the dx up here in the numerator, and then over x, which is just 3 tangent theta. Now, this 3 and that 3 can go bye-bye. Now this winds up becoming 9 secant squared underneath the radical, and therefore 3 secant. And that 3 secant combines with this secant squared to become 3 secant cubed over tangent. And I see secant and I see tangent, but that's just kind of frustrating because they're not in the location that I need them to be in order for it to be helpful for me. So sometimes, you know, you just have to make recourse to sine and cosine, get everything all canceled out, and then sort of recombine. Now, I'm dividing by sine over cosine, so it's the same as multiplying by cosine over sine. This cosine cancels with one of those, leaves that as cosine squared, and this becomes 3 secant squared theta cosecant theta d theta. And you're thinking to yourself, I've never seen anything like that before. How in the heck am I going to deal with something that has secant and cosecant in the same integrand? I'm so happy that you asked. I'm going to designate my u as cosecant theta. I'm going to designate my dv as secant squared theta. And the thing that tipped me off to this is secant squared d theta is a recognizable derivative. And when I get du, this is going to be negative cosecant cotangent d theta. So basically I've done trig sub, and now I've done trig sub into parts, and so this becomes 3 cosecant theta times tangent theta. I'll simplify here in just a minute. Minus, but see, this negative that's going to go in there is going to sort of unnegativize that minus sign, and it's going to be cosecant theta d theta. I went ahead and simplified that one because cotangent times tangent, they're reciprocals of each other, so by definition, yeah, they cancel each other out. Now, cosecant theta has a integral that is very, very similar to secant. It's just negative, right? Because remember, cosecant cotangent is like negative cosecant cotangent is the derivative. And so this, now cosecant is 1 over sine. Tangent is sine over cosine. The sines cancel out, and I'm left with 1 over cosine, or 3 secant theta. And then this becomes 3 natural log of, and actually this becomes negative 3 natural log of cosecant theta plus cotangent theta plus c. Now I need to do the recombining back. And I'm going to go ahead and draw my triangle up here since I've kind of run out of room towards the bottom of the page. Good thing I have a little space right here. And you'll have more space because you won't be writing this big. I'm writing this big because, you know, there's a camera looking down on my paper and I want you to be able to see it. So theta is here. This is going to be x and 3 and the square root of x squared plus 9, which surprises nobody. And we get 3 times the radical of x squared plus 9 over 3 minus 3 natural log of the square root of x squared plus 9 plus 3 over x plus c. And of course those cancel out. And this is over x because remember I'm dealing with cosecant, which is going to be hypotenuse over opposite, right, which is here, and then cotangent, which is adjacent over opposite. So opposite is your denominator for both of these, which is why you have an x. And unlike the one with secant, it's not numerical and you can't get rid of it. And so what we have, and you could split it into 2 logarithms, but, you know, why would you want to? And, you know, we'll just cancel out those 3's and rewrite it, and it'll be all nice and that'll be all nice and tidy. And that's it. That's kind of neat. Now, I was going to go ahead and do this one up here, but I think I think we all remember the fact that secant squared in the denominator becomes cosine squared in the numerator. Cosecant squared in the denominator becomes sine squared in the numerator. And if you have the integral of sine squared times cosine squared, you have to use power reducing for both of them. And then you have to power reduce again. We've done that problem. It was just one step away from this because this winds up being sine squared x cosine squared x dx. And you can go ahead and look back through your notes, and that is, so I'm not gonna burn time on the video doing that. What I would like to get to, however, is this problem. And we actually, in one of these videos, I forget exactly which one, we have done the Trig Sub version of this. I'm going to do it again real quick because this one asks you to basically do this integral in 3 different ways. Okay, so let's go ahead and do it by the first. Let's do it by Trig Sub. Okay, and the Trig Sub, of course, was x is equal to 2 tangent theta. That means that tangent theta is equal to x over 2. That means that dx is equal to 2 secant squared theta d theta, and we're going to go ahead and rewrite that integral. When we do rewrite that integral, what we get is we need to, of course, remember that x goes into here and is cubed, so it winds up being 8 tangent cubed theta. Now you're probably starting to remember this problem, times 2 secant squared theta d theta. And again, I'm going to do this version quickly because we've already done it. And it goes 4 plus 4 tangent squared theta. That, of course, becomes 2 secant theta. The 2's cancel. This, one of the secants cancels with this secant. And I'm left with 8 tangent cubed theta, secant theta, d theta. And of course, I'm going to pull one of the tangents out to combine with the secant. The last 2 I'm going to go ahead and change into secant squared. And what happens here is this is u squared, and this is du. So we wind up with 8 times 1/3 secant cubed theta minus secant theta plus c, and this becomes 8/3. And when you do the secant, when you do the triangle, the triangle is x over 2. This is square root of 4 plus x squared, or x squared plus 4, doesn't really matter. Basically, you wind up hypotenuse over adjacent. You wind up with the x squared plus 4 over 2 cubed. Well, that 2 cubed and that 8 are going to cancel out, and you're going to be left, of course, with 1/3, blah, 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 blah. But let's go ahead and do the secant over here as well, which is, of course, the same ratio. It's just not cubed this time. And therefore, I have 1/3 x squared plus 4 to the 3/2 minus 4 times x squared plus 4 to the 1/2 plus c. Now, we've done that. Now, let's do it by u sub. Okay, well, it stands to reason that if I'm going to do this by u sub, then my u is going to be the integrand. I mean, it's going to be the radicand, right? And therefore, du is equal to 2x dx. And remember that if I'm going to plug in for x cubed, right? Or I'm not going to type plug in for x cubed, but I am going to plug in for x squared. I need to do what I've referred to in the past as back substituting, okay? Basically, this x cubed needs to be pulled apart into x squared and x, right? So the way that we're going to construct it is we're going to say, okay, well, that's x squared, and that's x dx, and that's the square root of 4 plus x squared. Now, in order to get all of these pieces, I need a 2 right there and a 1/2 out in front. And now all of a sudden I can put everything, now I can put everything in terms of u. Okay, so the 2 and the 1/2, if you notice, are in red. They're new. The only thing that I've done is I've taken the dx, I've put it up in the numerator, and I've pulled one of the x's out of the x cubed and put it with the dx. That right there is my du. So I have 1/2, and then x squared, of course, is u minus 4 du over u to the 1/2. Well, that winds up being relatively simple. That is a monomial denominator. I can simplify. And what I wind up getting is I get 1/2. And of course, when I integrate u to the 1/2, it becomes u to the 3/2 over 3/2, or 2/3 u to the 3/2. And 4, of course, this u to the negative 1/2 becomes u to the 1/2 over 1/2, or 2u to the 1/2. That 2 combines with that 4 and makes 8u to the 1/2 plus c. Now what that means is that when I substitute back in my original variable, I get minus 4x squared plus 4 to the 1/2, because the 1/2 turns the 8 into 4 as well, plus c. And if you'll notice, that is identical to that. And the last thing that we have to do, the last thing that it asks us to do, is parts. And the parts is a little bit more difficult because kind of like the u sub, you have to pull it apart, but you have to pull it apart in a really unique way, which is of course why this is, extra credit. And so basically what happens is I need to pull it apart. I need to pull the x cubed apart again, okay? But what I'm going to do is I'm going to say, well, that's x squared, and then this right here I'm going to call 4 plus x squared to the negative 1/2 and 2x dx. So basically this right here is fully integrable already. It's u to the negative 1/2 du. So when I designate that as my dv, it's already basically set up and ready to go. So my u is x squared. My dv is this monstrosity. Let's see if I can do it without running out of paper. 2x dx. Haha. And then du is 2x dx, and my v winds up being, well, basically this is u to the negative 1/2 du, so it becomes u to the 1/2 over 1/2, or 2u to the 1/2, 2u to the 1/2. Fantastic. Now remember the 1/2 because it sort of comes along for the ride. And now I need uv, so 2x squared, 4 plus x squared to the 1/2, minus the integral. Well, one of these 2's I'm going to pull out in front. The other 2, you see this right here, 2x dx? See this right here, 2x dx? That's going to be pretty important to put right next to this. So I have 4 plus x squared to the 1/2, 2x dx. And now I have an integral that is integrable. And I have u to the 1/2 du. And the only difference from the original dv is that it was u to the negative 1/2 instead of u to the 1/2. Okay, well, fantastic. This is 2x squared, and I'm going to simplify here in just a little bit, but I'm going to get this done first. This is u to the 1/2 du. This becomes 2/3 u to the 3/2. So 2 times 2/3 u to the 3/2 plus c. Now that looks kind of like a mess, but let's go ahead and distribute that 1/2, and I get an x squared times 4 plus x squared to the 1/2 minus 2/3, and then I'm going to split this up into 4 plus x squared to the 1/2 times 4 plus x squared plus c. And the reason I'm going to do that is to show you that they're equal. okay? I mean, you could have just basically left it as 3 halves and just stopped right there. But I want to show you that these are equal. So I'm going to go ahead and factor out that 4 plus x squared that is common to both terms, here and here. And I'm going to sort of recombine what's in here. This is x squared minus 2/3 4 plus x squared plus c. Now, that becomes square root of 4 plus x squared, x squared minus 8/3 minus 2/3 x squared plus c. Or, and you can factor out the 1/3 after the fact if you want, that's 4 plus x squared, 1/3 x squared minus 8/3 plus c. Or, like I said, 1/3 4 plus x squared minus 8 plus c. Now, I want you to remember that because basically what happens is this looked a whole lot different when it came out because it was, I'm going to show you, I'll show you this right here, okay, there was no x squared anywhere, right? But the coefficients were also different. So what I've done is I've sort of recombined in order to give me a little bit, in order to basically, it's just a different way, it's just a different apportionment. I guess that's the best way to describe it. But if I take the original, the original answer, which was 1/3 x squared plus 4 to the 3 halves minus 4 x squared plus 4 to the 1/2 plus c. If I take the original and I reapportion it as well, go ahead and pull out that x squared plus 4 or 4 plus x squared, whatever, and I have 1/3 x squared plus 4 minus 4, but this is going to be in terms of thirds, so instead of 4, let's write 12/3. Okay? And so what we have here is we have x squared plus 4, 1/3 x squared plus 4/3 minus 12/3. And if we basically combine this winds up being -8. Oh, sorry. Okay. All I've done is just like the last one, I factored out the square root of x squared plus 4. Now, since there's 3 of them here, there's 2 left over. So this is x squared plus 4 to the 2 halves, which is just x squared plus 4. When I factor it out of this second term, all I'm left with is 4, but 4 can also be termed -12/3. Now I distribute the 1/3 and I can combine these into -8/3. So if I pull out a 1/3, and I'm just left with x squared minus 8 plus c. And that ought to look really familiar because that is exactly what I got here. Okay, boom, boom. Those are identical. So in terms of doing it all 3 ways, that is how you do it all 3 ways and get the same answer, though the third version, doing it by parts, unfortunately left us with something that had to be tweaked in order to verify that it was the same answer. But I think one of the reasons I wanted to do the extra credit problem is it becomes incredibly instructive to sort of watch, to sort of see something that can be done in multiple ways and then find the verification for that. And that's kind of what I wanted to demonstrate in all this. I've given you a whole lot. Okay, I've given you a whole lot, and I doubt that you'll wind up watching all of them. But I hope what you do watch is helpful. And as always, if you have any questions, please do email me. Bye.